Now we will discuss one important theorem. The theorem is the Kuratowski's graphs. K5 and K33 are non-planar. Already in the previous class, we got to know that K5 is non-planar. Similarly, K33 is also non-planar. But in this result, we try to prove those two results. So these two graphs are called Kuratowski's graphs. So first, we try to prove K5 is non-planar. Now our aim is to prove K5 is non-planar. But we assume, this is our assumption, we assume K5 is planar. K5. Actually, we need to prove K5 is non-planar, but we have assumed K5 is planar. Once if you assume K5 is planar, then by Euler's theorem, P minus Q plus R must be equal to 2. This has to satisfy. But in the graph K5, how many vertices are there? P equal to 5 and Q, number of edges. And already we know the graph K5. This is our K5. So, which has got 5 vertices and 10 edges. Okay. And one more thing. Okay. So, as we assume K5 is planar, by Euler's theorem this has to satisfy. Okay. But if you draw this one, it is highly impossible to consider this as a planar graph. Already we have got one result in the previous class with the help of this result. What is that? Q is less than or equal to 3p minus 6. This is a result which is for the planar graphs. Okay. Now if you substitute the value of p and q in this equation, what happens? 10 is less than or equal to 3 times our p value is 5 minus 6. So 10 is less than or equal to, it is 15 minus 6 is 9. So 10 is less than or equal to 9, which is highly impossible. This is impossible. When this is impossible, obviously K5 is planar is also impossible. It implies K5 must be non-planar. So therefore, which is a contradiction to our hypothesis. So K5 is non-planar. Now, similarly, we try to prove the other result, second one. Again, we consider K33 is a planar graph. K33 is a planar graph. This is our assumption. Again, we know the graph K33 contains how many vertices and edges. So this graph contains 6 vertices and 9 edges. If you observe this graph, if we try to embed this on the plane, what happens? So these two are impossible. It implies if you observe one face, so 1, 2, 3, 4 edges. It implies it looks like it is a triangle free graph. So one of the previous results, when it is a planar graph and it is triangle free, we got Q less than or equal to 2p minus 4. q is less than or equal to 2p minus 4. If you substitute the value of p and q in this equation, what happens? 9 is less than or equal to 2 times our p value is 6 minus 4. It implies 9 is less than or equal to 12 minus 4, it is 8. So 9 less than or equal to 8, it is impossible. So therefore, when this is impossible, K33 is planar is also impossible, or which is a contradiction to our hypothesis. So therefore, K33 is non-planar. So these are the two non-planar graphs and the least non-planar graphs called Kuratowski's graphs, and we have proved these two are non-planar. Just another concept of planar graphs called outer planar graph. Outer planar graph is also a planar graph in which it is embedded on the plane so that every vertex of G lies on the boundary of the exterior region. For example, I will consider this as an example. See, every vertex is lying on the boundary of the exterior region. Another example, this is an outer planar graph because it is a planar graph in which every vertex is lying on the boundary of the exterior region. Another example, here also every vertex of G is lying on the boundary of the exterior region. So these are all examples of outer planar graph. So what you can say, every cyclic graph is an outer planar graph. Even you can consider another example. This is a unicyclic graph. So unicyclic graph is also an outer planar graph because every vertex is lying on the boundary of the exterior region. We consider one more example. Now I will ask whether this graph is an outer planar graph or not. Then what you will say just by observation? So these two vertices are not lying on the boundary of the exterior region, it may not be an outer planar graph. But what I said, if it is possible to embed on the plane so that every vertex of G lies on the boundary of the exterior region, then that graph is called an outer planar graph. I try to redraw or embed this on the plane in this way. Okay, now this one, as I take it outside and I try to draw in this way, because location of the vertices and straightness of the edges in graph theory is immaterial. So I have redrawn the same graph in another way, in which all vertices are lying on the boundary of the exterior region. So therefore, this is also an example of an outer planar graph. Now, which graphs are non-outer planar? I will consider one example, K4. This is our K4. So this vertex is not lying on the boundary of the exterior region. If you try to locate this on the boundary of the exterior region, one vertex will be inside the interior region. So it is not possible to take all the vertices on the boundary of the exterior region. So therefore, this is one example of non-outer planar graph. Similarly, we will take another example. This one. Again, is it possible to take this vertex outside the or on the boundary of the exterior region? No. Even if I try to redraw this, if I take this outside, if I redraw, so these two vertices will be inside. So therefore, it is not possible to draw on the plane so that all vertices lie on the boundary of the exterior region. So therefore, these are the examples of non-outer planar graph. Now we will think of another concept, maximal outer planar graph. Maximal outer planar graph is an outer planar graph in which it is not possible to add one more edge. If you add one more edge, it violates the property of outer planarity. For example, I will consider one example. This is an outer planar graph. Is it maximal outer planar? Maximal outer planar means an outer planar graph in which no edge can be added without losing outer planarity. But this is an outer planar graph, even though we can add one more edge, even though it is outer planar. So it implies it is not maximal outer planar. Again, if we add one more edge, even though it is outer planar. Now we will add one more edge, even though it is outer planar. Now is it possible to add one more edge without violating the outer planarity? These are the two non-adjacent vertices. If I join in this way, this vertex will be inside the interior region. Even if I join these two, this vertex will be inside the interior region. So we can't add, even if we join these two vertices, so this vertex will be inside the interior region. So now this is an example of maximal outer planar graph because you cannot add one more edge. If you add one more edge, it violates the outer planarity condition. So this is one example. Now we will prove one important result on maximal outer planar graph as a theorem. Let G be a maximal outer planar graph. Let G be a maximal outer planar. Instead of taking planar, I shall take plane graph, outer plane graph with P greater than or equal to 3 vertices, greater than or equal to 3 vertices. Then G has G has P minus 2 interior faces. This is the result. For example, we try to verify this result. So this is an maximal outer planar graph with a P greater than or equal to 3 vertices. Then G has P minus 2 interior faces. How many vertices are there in this graph? 1, 2, 3, 4, 5, 6. So there are 6 vertices. Now P minus 2 will be 4. 6 minus 2, which will be 4. So there must be 4 interior faces. Let us see. 1, 2, 3 and 4. So these are the 4 interior faces. So the result is true in this case, of course. Now we try to prove the result. Suppose P equal to 3. So we prove this result by using mathematical induction on P. Suppose P equal to 3, then obviously the maximal planar graph with 3 vertices is K3, or you can say C3. And already which has got 3 vertices, so 3 minus 2, it is 1. So obviously there is only one interior face. It implies in case of P equal to 3, the result is obviously true. So next we try to assume the result is true for P equal to K vertices. This is our assumption. Assume that the result is true for P equal to K vertices. It implies which has got how many interior faces? K minus 2 interior faces. Okay. With this assumption, we try to prove the result is true for P equal to K plus 1 vertices. P equal to K plus 1 vertices. Okay, we try to prove this result. And M interior faces. So what we have considered? Suppose P equal to K plus 1. So the graph contains K plus 1 vertices and it contains M interior faces. So what we need to prove? We need to prove M equal to P minus 2. This we need to prove. Okay, let us think of this. Now we consider a graph which is, of course, maximal outerplanar graph. Suppose this is an example already. It is there on the board. Let V be one vertex, which is a maximal planar graph, and it contains a vertex V of degree 2. Then, if I delete V from G, what happens? Then the G graph G minus V, it will be this graph. For example, okay, this is the graph G minus V. Okay, so the graph G minus V contains how many faces now? Then the graph G minus V has how many interior faces? Earlier it has got M interior faces. By deleting one vertex, the graph G minus V has M minus 1 interior faces. And how many vertices this graph will be having? Earlier it has got P equal to K plus 1. After deleting this vertex, the vertex which you have deleted from this graph G, so the graph G minus V has how many vertices? P equal to K vertices. K vertices. Because one vertex is reduced here. But by inductive hypothesis, when the graph has K vertices, the result is true. That is inductive hypothesis. It implies M minus 1 should be equal to K minus 2. K minus 2. Which implies M equal to K minus 2 plus 1. But what is K? Our K is P minus 1. So which implies M equal to, actually instead of K I should write P minus 1. This is minus 1. So therefore it is equal to, what I did, K equal to P minus 1. Of course, P minus 1. Then this minus 2 plus 1. Why I written this minus 1? I don't know. Okay. Anyway, so it is minus 1. So therefore M equal to P minus 2. So this was the result we need to prove. So we got it. So therefore it has got P minus 2 interior faces.